Alright. Hi guys. Today we will review the final exam, and basically I will go over the practice exam here. And if you have a question, just let me know. You can stop me. So the question 1 is about the true and false question, and here the first question asking about the in N-type silicon, the dopant is a group 3 elements, but the answer is false because the N-type silicon is a group 5. And the second question, in PN junction, the built-in potential barrier is reduced when the reverse voltage is applied. So if you record the PN junction, is something that looks like this. And here on the P side, here on the N side. So here it says the negative voltage to the P side. So here we apply negative voltage, and it will pull up the band here, the P side. So it looks like something like this, which means it increased the built-in potential. So the answer is it is increased. So the answer is false. Number 3, the increasing doping density of the MOSFET will increase the onset current. There is a relationship between the NA is proportional to the VTH, which is threshold voltage. So as we increase doping density, and when that means we increase threshold voltage, so it will decrease the on-state current. So this one should be decrease, and so the answer is false. Number 4 is increasing temperature. The off-state leakage current of the MOSFET will increase. So you can use the either equation, off current equation, or you can use S is something proportional to 2.3 kT over Q. So this is inverse of the slope. So as we increase the T, we increase S. It means we decrease the slope. So if you recall the exam 2, we had some question related to this. So let's say we have some temperature here, T1. As we increase temperature, then it looks like something like this, T2. If T2 is greater than T1. So at the off state, we increase the leakage current as we increase the temperature. So number 4 is true. Number 5, decrease the power supply voltage, VDD. The CMOS inverter delay will decrease. So if you recall the tau, the delay is C times VDD over ion. And also the ion is in saturation region, we have a VDD minus BT square. So bottom we have C over VDD. If we say VDD square is cancelled out with the VDD, then as we decrease the VDD, it will increase the delay. So delay should be increased, and so the answer is false. Number 6, in constant voltage scaling, the chip active power density will increase the subsequent generation. So this one was in the homework 5, and in the homework 5 we had a same condition to keep the same VDD and VTH. So we have the power density is proportional to, see the scaling factor alpha cube, So as we move to the next generation, the power density will increase. The answer is true. Number 7 is a DRAM needs refresh due to the leakage current to the storage capacitor, and refresh is done by write operation. The answer is false because refresh is done by the read, and then we do what we call write back. So the answer is false. Number 8 is compared to the L3 cache, L1 cache uses smaller size of transistor in the SRAM transistor. So L3 to the L1, we want something faster. So we want faster, which means we have to have something larger, W over L. So here the answer is false, and it should be larger. And number 9, flash memory has finite cycling endurance, thus its lifetime is limited. Yes, this is true because when we write flash memory, we store the electron, and when we erase it, we have to remove it. We have some physical damages when we do some such operation, so which causing the limited lifetime. So the answer is true. And the floating gate transistor has a larger threshold voltage when more electrons are stored in the floating gate. Yes, this one is also true. If you recall the flash memory program and erase state, you can see this one in the homework 5 as well. This one we have erase, and this one is a PGM program, and it has different threshold voltage. It is because when you program, you store the electron inside of the gate, and that causes harder to invert the transistor. So which is the same as we shift the threshold voltage, and so the answer is true. And here the question 2 is asking about the P-type MOS capacitor. So we typically deal with the N-type MOS capacitor, and here you have to care about, because this one is P-type, it works just opposite. So let's go over the question 2.1. At Vg equals 0, to calculate electron density N and the hole density P at the point A. Here, the point A here. So here you use the ND is already given. Since the gate voltage is 0, so it's N equal electron density is equal to the ND is a 10 to the 16 centimeter minus cube, and P is hole density. We can calculate from the NP product. So Ni squared over N is a 10 to the 20 over 10 to the 16. We get 10 to the 4. And question 2.2 is sketch the MOS Venn diagram here. But you have to keep in mind this is P-type. So one thing you can do, you can start from equilibrium state. So I would say we have MOS, we have EF, and we have EC, and we have EF, and EI, also EV. So EI is where the midpoint of the EC, between EC and EV, and EF, because since we are talking about the P-type, so EF should be near the EC, see, above the EI. And then if we apply the negative voltage to the metal gate, then it will pull up the bend, something like this, and this one also goes up, and it will bend something like this and that. Oh, not this one. Okay, something like this and that, and you will get the pretty much similar as shown in here, the answer. And question 2.3, at Vg equal the threshold voltage, which is inversion. So to calculate the electron density N and the hole density P at the point A. The point A is the is located here. So point A. So we have a strong inversion at the surface, and so which means the P and N is the density is flipped. So P is equal to 10 to the 16 and N is 10 to the 4. And question 3 is about the scaling. So here we have all the physical dimensions downscaled by factor of x, and then the VDD and VT is decreased by y. And here the first question is asking about in the next generation, the total number of the transistors doubled. If total number of transistors doubled, what's the value of x? So what's the scaling factor x? So the first thing you need to do is you need to calculate the number of transistors. We here denote it as NN is equal to, this one is total area, and this is a transistor. So width times L is the length is the transistor. So you divide by that, you will get the total number of the transistor. But then for the next generation, so we substitute that as n is n plus 1 is equal to, since it increased by 5% in every subsequent generation, we multiply A times 1.05, and also because the W and the L is scaled by X, so we divide by X, and you will get that 1.05 X squared and NA. And we can find some ratio between next generation and the current generation, and NN plus over NN is equal to 1.05 times X squared, and we want this to be 2 times bigger, and so we will put 2 and solve for X, then you will get around 1.4. And second question is asking about the ratio of the power between the N and N plus generation in terms of X, Y, and frequency. So we first start from the single circuit level. So we have to find the load capacitor, and the load capacitor is Cox times W times L, and we know that Cox is a C0 times Cox over Tox times W over L, as shown in here. And so for this one, we want to calculate CL n plus 1 generation is equal to Cox n plus 1 times W n plus 1 times L n plus 1. This one is basically the C0 and C epsilon ox, and won't be changes. This is given value, and T aux is scaled by X, and W scaled by X, L also scaled by X, and X is cancel out here, and you will see this one is the same as this one, and we have CLN times 1 over X. So our goal is finding the power. So here the P is equal to CLN times the VDD square times the frequency. And the next generation will be Pn plus 1 is equal to Cn plus 1 times, here we have scaling factor y for the VDD. So we have a VDD square over y square. And we have a frequency n plus 1. We know that this CL n plus 1 is equal to this one. So we plug in this CL over X, and we have VDD square over Y square, and we also have a frequency Fn plus 1. So from this, we got this P, and we do have this one too. So you can find the ratio between Pn plus 1 over Pn. If you calculate, then you will get this relationship right here. But this is not the end, because this is for the single circuit. So if you want to find the total chip level, we need to multiply this by total number of the transistors. So the power here, total power will be number of transistor times single circuit. Here we know that the nn plus 1 is equal to 1.05 x squared from the previous calculation here. So we plug in that, and we plug in this one, and we already define this one as our single power, and we have number of transistor Na here. And finally, you can find the ratio between the P total n plus 1 over P total n. Here we have a 1.05x over y squared times Fn plus 1 over Fn. So third question is, what is the relationship between Fn plus in Fn if you wanted the total dynamic chip power to remain the same across the generation, which means you want to have a ratio equal to 1, and we found the relationship x and y and frequency from the previous question here. And so we know this relationship, and we can solve this for the frequency ratio, and then you will get y squared over 1.05 times x. So number 4 is asking what should be the value of y if the clock frequency is constant, which is the Fn plus 1 and Fn is equal to 1. We already found that x is 1.38, or you can say 1.4, and we plug in the x equal to 1.4 or 1.338 and solve for the y, then you will get 1.2 as for your answer. Number 5, in recent years, why is it difficult to reduce the subthreshold voltage? The answer is because we want to maintain the subthreshold slope greater than 60 millivolt per decade. This one allows us to have a sufficient on-off ratio. We need to have some margin, so that's why we want to keep it greater than or equal to 60 millivolt per decade. To do so, if we cannot decrease the threshold voltage aggressively, because if we do so, we will not have a threshold slope greater than or equal to 60 millivolt per decade. So you can just say subthreshold voltage should be greater than equal to 60 millivolt per decade to make a sufficient on-off ratio. And question 4 is asking about the SRAM. And the first question is we have to calculate what's the current flowing through the transistor PG1. PG1 is right here. And you see, first thing you have to identify is whether this is the saturation region or triode region. So here you VGS is here, N1 node here is raised up to the 0.17, and you have 1.1 as a BDD. So you have VG minus BS equal 1.1 minus 0.17 is 0.93, which is much greater than BT here. BT is here, is 0.2 all the way. So you can use ID equal to beta over 2 VGS minus VT square. If you plug in, the beta is already given, and the VGS and VT is also given. So once you plug in, and you can get 20.78 microamp. The second question is asking about the read sensing time, and the delta V voltage change on the baseline, and capacitance is already given, and the equation you should use is T equals C times delta V over I. And if you plug in this 100 femto and 100 microvolt and the current we already calculate above the first question, we use 20.78 microamp, then you will get the value 0.48 nanosecond. So, and third question, they're asking about what are the off current for the NMOS and PMOS, and here the ratio is W over L is 1 and 1, and here the value, the slope, subthreshold slope is 70 millivolt per decade, and we know that the subthreshold voltage is 350 millivolt, and we also know what's the subthreshold current here. It's 1 microamp, and for the PMOS is 0.5 microamp. So it's exactly the same as in your homework question. So 70 millivolt per decade to the 350 millivolt. We have 5 orders smaller, so which is 10 to the negative 5. So we know that I sub is for the PMOS. For the PMOS we have 1 micron. So we calculate this by multiplying this factor, and you will get 10 to the 11 is 10 to the 10 picoamp. This is for the NMOS. PMOS you just use 0.5 times 10 to the 6 and 10 to the 5, you will get 5 picoamp for the PMOS. Question 4 is asking for leaking transistors. Although we are in the hold mode, the SRAM is still suffering from the leakage current. So we need to figure out which transistors are leaking. So the way you can do is you can analyze the some imbalance between source and drain. So for example, if you have, let's say, the NMOS is, the gate is 0, this is source and drain is like 1 and 0 volt. If we have some difference, although the gate is turned off, you will see some leakage. So for example, the PG1 here, this side is 1 and this side is 0. Although this is NMOS, so even if we apply the gate voltage as a 0, you will observe some leakage current here. So this is this transistor is leaking, and PU1 here is VDD. So let's say it's equal to 1, and the other side is 0. And this one, since this one is PMOS, if we apply 1, this one should be turned off. The thing is, this we have this much difference, so this one is leaking as well. So here also PD2, we have 1 volt this side, and the bottom side we have 0, and this NMOS is 0, so it should be turned off, but because we have some differences between these two, we will see some leakage. So PD2 is leaking transistor. So PG1, PU1, PD2, these three are leaking transistors. And number 5, consider the W/L ratio of the PD, PG, PU is 2 to 1 to 1 ratio. And also the 4 megabit SRAM. So we have to calculate total leakage power consumption. So power consumption is P is IB, but we have to calculate this off current. And since the PG1 is W/L is equal to 1, and it's NMOS, we already calculated here is a 10 picoamp. So we use 10 picoamp for the PG1, and PU1, the W/L is 1, but this one is PMOS, so we use 5 picoamp. And for the PD2, W/L is equal to 2, so we have to multiply by 2 to get 20 picoamp. So if we add up this all, then you will get 35 picoamp. But this one is only for one single SRAM cell. So if you want to calculate in array, then you have to multiply this by 4 megabit. So 4 megabit times, and also we have to know what's the VDD. VDD is equal to 1.1 times, and total of current is 35 picoamp. So you will get 0.154 milliwatt. So question 5 is DRAM and 3D NAND flash. So first question is asking about the sensing margin. Sensing margin, you know that we do have some equation for the sensing margin, that is delta V equals CS over CVL, VL, and CS times BDD over 2. And we need to calculate this CBL. The way we can do is a CBL per cell is already given. In each bin line it has 1024 cells, so we multiply 0.1 femto farad times 124, then you will get 102.4 femtofarad, and you plug in the numbers. The CS is given 25 F, and 102.4 plus 25, then you divide by 1.6 over 2, then you will end up with 157 millivolt. If you see some question like this, please put your equation so that we can give you some partial credit even if you don't get the correct answer. So as you can see from if you see the rubric, once you have this equation you will get half point, and if you get the right value then you will get half point and you will get the full credit for that. And the second question is asking about how much percentage of time is used for DRAM refresh. So here the refresh period is 64 milliseconds, and one DRAM array has 8K row, which means row to row refresh interval should be 64 milliseconds times 8K, which is 8 microsecond. So every 8 microsecond we have to move around and have to do some refresh. And we know the row cycle time is 40 nanosecond. So we divide 40 nanosecond by 8 microsecond, and you will get 0.5%. And third question is asking about what is the memory capacity of this 3D NAND chip. So memory capacity, and if you see, it says 64 layers, which means this is Z-axis. We have 64 layer, and also says 1024 bin lines and 1024 string. So which means this one is 1024, and also this side is 1024. Basically you have some cube, and 64 by 1024 and 1024. But this entire thing is just one block. Since we have 1024 blocks, we have to multiply this by 1024. So I would say 64 layer times 1024 times 1024 and times 1024 blocks. Then you will get the capacity, but you should keep in mind, because each transistor is 2 bits per cell. So it's given here. It's 2 bits per cell. So you have to multiply by 2. So you will get 128 gigabit, and that's your answer. And the last question, what is the estimated array efficiency of this 3D NAND chip? Now you all know that the NAND flash has peripheral circuits, and the array. So we already calculate the capacity, but then if you see when you calculate the area, you will see this NAND string. In fact, this one will something looks like this, the fila, yeah. And this one only occupies 2 by 2 area. And when we calculate the capacity, we take account this 64 layer, and also each transistor we say 2 bits per cell. So we have to divide by this layer and B per cell to get actual the area. So to do so, we can do 128 gigabit times 2 times 2f times 2f, and divide by 64 layer and the B per cell. And here the F is 50 nano. So you can use 10 to the this one just automatically cancels out, and 10 to the 9 times 50 nano times 50 nano, then you will get 10 millimeter square. And total area is already given. The area is 25 millimeter square. So area memory divided by total area will be 10 over 25, which is 40% of the total area. So area efficiency is 40%. Okay, that's it for the practice exam. If you have a question, you can ask.